Thank you for this splendid opportunity. So I will be talking to you about information theory or physical vitalism. It's not as bad as it sounds. Perhaps, or if you have no philosophical background, then you don't know you should be worried about this kind of title. So perhaps I just skip it. So this is me. So after I got or left my office, I have been free to do research, and it is you will see it is not bounded by some traditional practices, I would say, and this is the result of those studies, this book. And I also want to introduce this Petri Lievonen, who is behind many things. For example, now he is behind the camera. And he's working at this Helsinki Institute of Information Technology, so he's much better accessible to you if you are interested in these issues. These are some simulations he has been carrying out on these algorithms. So let's start about the very, very basic or first principles. You know that or in science we are today doing empirical science, or we are taking data and then we try to model it. But the problem today is that we have so much data, and there are so many different kinds of models. We are totally lost in that jungle. So we would like to have some firm background to know some basic model structures that we should or could be using. But the problem is here that if you make some assumptions about what are good models for real life, or what the world is like, then it's philosophy or it is metaphysics. And that is not very scientific to start with. But it's very, I would claim that it's this kind of thinking is fruitful anyway, because you can recognize that now we have been kind of thinking in the very analytical way, or in the spirit of analytical philosophy, really, or in the spirit of early Wittgensteinian philosophy, so that all things that exist, they are facts about reality, and everything can be expressed in formulas. But later, Wittgenstein observed that not everything was said in that Tractatus, and really the interesting things are just kind of, they are like flowing in the flow of life, as he said. Now, we still have some background here if we try to go or approach things in different way. So if we start from the assumption that everything is motion, then we have this process philosophy available. Unfortunately, there are not very many tools available there, but then we can start applying our engineering tools or engineering intuition here. And we can simplify this issue of motion or change to its very basic constituents. And in the beginning, all movement, it's some kind of vibration only. Only when it gets coordinated, then you have some flow, this process, philosophical flow. So let's start from vibration. And another assumption is that because this dynamics is so much more important, we assume, then all structures and mechanisms, they are forgotten to begin with. We assume there's no structure in the world to begin with. So what can we know about the world? What is there still available to us if we have no structure and only some vibration? Now I want to say a few words about this vitalism, because if somebody knows what this vitalism is, it is really trying to find some forces that pull things towards itself. But now we are not trying to find purpose or finalistic explanations. We are just modeling vibration from the beginning and study what happens when it starts coming out. So this is, if we have no structure, then we know that the distributions are Gaussian. This is all we can know with those assumptions we made. And the traditional starting point is that we concentrate on the mean. But the problem is that then we end up with the very normal models about the world, the static world, where you have just these some kind of mean values. And very much this distribution or this kind of variation around the mean has been forgotten. And now it is assumed that this variance here, it is not only measurement noise, but it contains the essence of that motion or vibration here. And this all becomes more interesting or more relevant in higher dimensions, of course. So let's repeat the starting points. Now we assume that what we can normally observe in a static view, it is, let's call it matter. It's the result of coarsening or forgetting about details. But now we define this information as the second moment of the distribution. So if you want to have it zero mean, then you have this variance. And if you have high dimensions, then you have correlations and covariations. And this is intuitive motivation for this study. Because if you assume that everything in the world is some kind of springs, and the state of a spring, it is the variable z, then you know that the energy of that spring, it is proportional to z squared. And if you have this kind of measure for energy in the world, then you have some kind of semantics, meaning that it is only this kind of energy that can make changes in the world. And if you know where there is much energy, then there is some kind of meaning in that portion of the world. Okay, for some other audience, I would say that this can be intuitively identified with some kind of technical or physical vital force. And starting from this kind of starting point, you can see that you can skip from how questions to why questions already, or you can start studying more or some kind of deeper questions. And this is the explanation for introducing a new term. Instead of those expectation values, we are now employing that kind of emergency operator, that big epsilon, because that expectation is mathematically, it is very difficult concept, because you would need all history, all data simultaneously to determine the expectation value. But this emergency operator, it's enough if you know the history just up to this point. And it turns out that if you have different kinds of frequency bands there, then it gives rise to different kinds of models or some kind of fractality to structures. Now I will just once more explain what is going on here when we model information. Normally, when you do science or when you do something with nature, you apply your interpretations from above. So your kind of semantics is given by your mind, given from upside. So you have to do it by hand for all items separately. But now we let this information come from below, and then when it comes to the top level, you can perhaps, if it's really relevant, then you can perhaps find also connections to mind level phenomena or mind level concepts. So if we want to have some background here, we can notice that in cybernetics, for example, Gregory Bateson has defined that what is interesting is differences that make difference. This is information, actually. And when we now start getting further, we need to have some connection for items, or how things are connected to each other. And for that purpose, we can actually start from that Bishop Berkeley saying that to exist is to be measured. So this is what we here apply. Because if you want to have much information, if you want to make your mark in the world, then you need to have much information from your environment. And making your mark, it is applying that information in your environment. So surviving and flourishing, it is the same thing as being in interconnection or communicating with your environment. So what remains, or what best can do this? It will remain the most visible in the world. So technically speaking, we can follow the flow of information, optimal flow, and assume that it is the winning strategy in the world. Okay, then we start modeling that interaction first. And here we are, or we can take, for example, chemical reactions as our starting point, because there you also have this chaos around you, and the net result, or the chemical reaction rate, it is the result of some kind of collisions there. So you know that the net result is linear, actually. So the activity X is a linear function of variables in your environment. Actually, what the derivation on the previous slide was only to motivate this linear form. Because actually you already know that if your information is defined as a quadratic function, then you need to have linear formulations to maximize it. So this is just a motivation. This can be seen as some kind of generalized diffusion also. So now we define the information theoretic system as a set of this kind of X variables or state variables that see the same kind of environment or vector Y. And now we need mathematics to follow this information flow. Because using natural language, you only can, or you are not able to do dynamic things very well and so on. And what is most important is that now your attitude to mathematics kind of changes a bit. Because typically mathematics is used free of semantics. You only apply syntactical structures, manipulations. But now we only follow that information. So the semantics is bound to the structures to start with. So we are not studying all mathematically possible structures, only relevant structures, hopefully. So now it's easy task to when we start from that linear formulation to find the maximum for it, or find first the expression for information. You multiply by X on both sides and then take the expectation or that emergence operator. And it turns out that Lagrange technique gives you this kind of formula for those A's, meaning that finally the interaction between the system and the environment is given by this formula, where you have first this Q, a coupling matrix, diagonal, where these elements tell how tightly coupled the states are. And then you have this kind of semantic filter also there. Let's skip details here. It's rather easy task now when you start studying this formula and when you study when it is, what kind of stationary or what happens if that X outside of that operator and inside of that operator, if they are the same. So you apply emergency operator to this formula, and you will recognize that you will have something that reminds principal component analysis. And indeed, it does principal subspace analysis. It can be proven that it really concentrates on the most significant of the data variance directions or information directions in data, really. And the funny thing is that if you look at the formulas, you see that the observable environment gets modified in a very funny way. If the original eigenvalues of environmental information, they are given on that envelope, then you will have those coupled eigenvalues having very different structure. The most important of those eigenvalues get modified, but I will not go into details here. Okay, that information thing, it is very much correlations based, and it's if you go through those Hebbian algorithms, you notice that they are also correlations based, and they always have the stability problem, so that the structures are not stationary or stable. And here we want to keep structures linear, and we can keep things linear when we apply linear negative feedback to implement that stabilization. The problem here is, of course, that when you have multi-level dynamics, you will have simulation problems. In real life, you will not have such problems because it is simultaneous. When you use something, it is implicit that you also exhaust it. But in simulations, applying information technology, you need to take into account that exploitation separately, and then you have multi-level dynamics. Okay, this is an example of what can result. So the red arrows here, they are this information flow. So if the plants, they grow differently in different years. For example, some plants like sun, some plants like moist. It means that in different years there are special covariation structures in the plant world. And it is that structure that gets modeled by these information theoretical models. And it can be claimed that ecological lockers are based on those structures. And it needs to be recognized that if you have nonlinearities, then the basis functions, they get turned towards sparse components typically, as simulations show. And the blue arrows here, they show the normal visible matter flow, meaning that the levels in plants or levels in resources, they are reflected in abundance and biomass on the higher level. But this is not the whole story, so that it would only, or the higher level would just reflect the lower level. Actually, the most important, interesting thing is this backwards arrow. What the coupling does to this environment, really. and it turns out that it can be called regulation. When you write down the formulas for those resulting mappings, you see here the normal phi. It is the mapping from the observable environment in stable state to the state, and the other phi, var phi, it is the mapping from the original undisturbed U to X. Then you notice that you have very strange dual symmetry there, because you can recognize that these mappings, they take the form of ridge regression simultaneously in the different or looking different way, or when the data goes in different way, it turns out that principal subspace analysis is implemented, but in a different way the same mappings implement regression, optimal in the sense of information capture or variation capture. So there's optimal modeling and optimal estimation, and when you apply that negative feedback, it's optimal control, really. But you can see here that it is not really optimal, this regression. It's only robust, because it's rich regression. So not all information is exhausted in the environment. And when you study the behavior of the inherited information, you can notice that there is some level of coupling, or that Q parameter you must have. If the value of Q is lower, then there can be no coupling, and in steady state your system dies. But interesting behavior starts only after that. You have now some or plenty of free parameters, but you can also, applying the same principles or optimality principles, you can apply methods for determining the variables. For example, the system size, or the size of n, it has some optimal value based on the singular values of the data. And here is an example of what things looks like, or what things look like. There are some handwritten characters or digits, and then it is a 32 times 32 grid, and this is what happens. If you don't apply some non-linearity there, then the results are less specific, or you have mixed features there. So it converges to this kind of outlook. So this is very much like, or what you have seen in different kinds of algorithms also. So you can assume this is something that perhaps the visual cortex also does on the bottom level. There are interesting connections to different kinds of machine learning algorithms. For example, starting with Hopfield nets, you again have some cost function or energy function there. And if you take restricted Boltzmann machines, then you can recognize that you again iterate the signals because you have this loop there. And actually in this case it implements black noise, or it gets rid of the extra noise there, and it makes modeling easier. Then there are these Hebbian algorithms and so on. But especially if we take multi-layer perceptron networks, we can recognize that there's very interesting difference here. Because typically you remember these perceptron networks, there you have the problem that they are physiologically not very plausible because you have to backpropagate the error. But here it is only error that is all the time manipulated on, or these x bar, u bar values, they are errors, feedback errors. So it is kind of very different kind of signal flow diagram that comes out. You have difficult signal propagation, but very easy model adaptation, because it is directly those signals that are visible that are used for adaptation. And these worlds there, they will come, or we will meet them again later. Okay, if you assume that there is some evolution or something, that if systems want to get more information to the higher level without dissipation, then it turns out that if they can recognize the neighbors, if there's internal feedback, there's no need for feedback from outside, from environment. And then it turns out that you can implement exact least squares regression. And for that kind of models, you can easily find different interpretations also. Because if you define this kind of an error or energy function, you can recognize that if you differentiate with respect to x, then you notice that the solution is the same as on this slide. And we started with optimizing or maximizing information on the low level, and it turns out that when we look from upside, it minimizes information. This is interesting because there are connections to different kinds of macro level of modeling techniques. This optimality criterion can be written in different forms also, and this features-based formulation is interesting because here, if you compare to standard traditional maximum likelihood criterion for Gaussian data, you recognize that this data covariance, essentially, you usually have inverse of data covariance here, weighting. Now we have direct data covariance. And this makes very much difference with respect to what kind of models you have. Because it turns out that you all the time concentrate on the freedoms. You are not trying to find the matching of the rigid structure. You try to get away from the given structures all the time. This makes very much difference in interpretations. So I will skip the rest of those discussions, but I will just show another kind of open-ended challenge here. Because if we start thinking of what are the fine details of the dynamics of how the system converges, then we can recognize that if we apply expectation maximization in the form of ensemble-Kalman filter, we can recognize that the best way to adapt those system states is this kind of dynamic formulation. Or here is the dynamic formulation. And if you continue assuming that the inputs to the system, they are other states from other systems, they are also dynamic, having the same dynamics. You can recognize that you have two states that feed each other, but there is minus sign. You can recognize that the end result is an oscillator. And this was a non-dissipative model, so it's non-vanishing oscillation there. Okay, in the book there was a mistake here, because this is only for scalars, but in normal case you need to take this eigen value at the time. So another qualitative leap is that when you start studying the frequency domain, when you assume that all systems, they oscillate, you have some kind of vibration fields and they interact. You have very different kinds of structures. But the nice point here is that they are again linear, and you have strong tools for them. But this possibility has not been studied very much. Okay, finally there is one catch for you, because you are information theoreticians. So, what is the difference between information and information? We started from chaos, and we started applying these life processes. I call them these information theoretical processes, I call them life processes. They start separating this chaos to noise and model. And when it has exhausted all information, it ends up in dead model structures, where you have plenty of or high level of Shannon information. And on the other hand, you have high level of Shannon information in the remaining white noise. So the last, or related to the previous slide, if the system is this kind of living creature that eats that chaos, where you have possibility of model and you have possibility of information, it changes to rigid structures and noise, and it defines the boundary line between order and chaos. If order is that rigid structures and chaos is that chaos with no model yet. And it's no wonder why living systems or complex systems remain on the boundary line, because they define the boundary line between order and chaos. So this book here that is available now, it is really about life in general. you remember those worlds in the structures. It is assumed that these kind of control structures that are information pumps, they are the basic structures in living organisms, in universal living organisms. And starting from that control paradigm, you can also observe that the environment, when it gets controlled optimally, it turns out that it goes towards maximum or actually minimum variation or heat death. So in the world of that model, the entropy grows maximally. So even if the system gets more and more complicated, it turns out that the environment becomes better and better controlled, and its entropy level goes higher and higher. So there is no more kind of contradiction here, as it usually is contradictory, that natural systems seem to become more complicated. So, thank you. This was all I wanted to show you, but I have plenty of other slides if you are interested in some special issues.